Example: show that the minimal polynomial of a normal operator on a finite dimensional inner product space has distinct roots. Solution: let p of x be the minimal polynomial of a normal operator T on a finite dimensional inner product space V. Then, by the definition of minimal polynomial, p of x is the monic polynomial of the least degree that annihilate the t, that is, for which p of t equals to 0, we shall show that p of x equals to x minus c1 so on into x minus ck, where c1, c2 and so on ck are the distinct complex numbers. Let c1, c2 and so on ck are not all distinct, that is, let sum of roots of c of p of x is repeated, then p of x equals to x minus c whole square g of x for some polynomial g of x. Now p of t equals to 0, which implies t minus ci into g of t equals to 0, which implies t minus ci whole square g of t equals to 0, which implies t minus ci whole square into g of t alpha equals to 0 for all values of alpha belongs to V. Putting u equals to t minus ci, since operator t is a normal and x minus c is a polynomial with a complex coefficients, therefore t minus ci equals to u is a normal operator. Now let alpha be any vector in V and let beta equals to g of t alpha, then u square beta equals to u square gt alpha equals to t minus ci whole square g of t alpha equals to 0. Since the operator u is a normal, therefore u square beta equals to 0, which implies u of beta equals to 0, which implies t minus ci into beta equals to 0, which implies t minus ci into g of t alpha equals to 0 for all values of alpha belongs to V, which implies t minus ci into g of t equals to 0. Thus the operator t annihilates the monic polynomial x minus c into g of x, and the degree of this polynomial is less than that of the p of x. Therefore it contradicts the assumption that the p of x is the minimal polynomial for the t. Hence no roots of c of p of x is repeated. Therefore p of x has distinct roots.